parts of the world. It's called From the Pendulum to Dark Matter. Slightly cryptic title, but it starts with that man Galileo. So Galileo was studying medicine in 1851, and he was actually bored in church one day and used his pulse as a stopwatch to time the chandelier that was blowing in the wind backwards and forwards. Must have been a very boring sermon, I think. And he noticed something rather curious. It didn't make any difference whether the chandelier took a swing of a short swing or a long swing to the amount of time taken for it to return to its original position. So the longer the swing, the faster it was moving, and it always came to the same time. And he thought that was rather curious. And being a good scientist, Galileo went home and tried it out. What he did was he got two pendulums, each of the same length, and realized that they kept time regardless of various factors. It didn't matter what the size of the sweep was of the pendulum, nor did it matter what the mass of the bob, the lump of lead on the end of the string, was. And in fact, he went on to realize that the thing that mattered was the length of the string, and he realized that the square root of the length of the string controlled the period of the pendulum, so came out with a mathematical formula for it. And it was another 100 years before Christian Huygens, after whom a space probe that landed on the moon of Saturn called Titan was named, used this to actually make clocks, to make the pendulum clock, the first really rather accurate timepieces. Now the second part of this story, really then we jump forward a little bit to Kepler. And Kepler, a very famous scientist for analysing the orbit of the planet Mars based on his boss's data. His boss and his mentor was Tycho Brahe. And what he was trying to do was work on the idea of Ptolemy and the fact that all of the planets moved around the Earth in circles. And the system was getting more and more complicated, with circles on circles being added, as in the diagram here. The little pink planet is doing a circle mounted on another circle that's moving around point X in the center, and even tried it with having the Earth offset away from that central point. But no matter what he did, he couldn't make things fit. Just no way to make the data meet the observations. Eventually, he decided to abandon the use of circles, as you probably all know, and came out with his famous first law. What he thought about was that perhaps the power of the sun was somehow weakening with distance, and so that planets would speed up near the sun and slow down while farther away as part of this investigation. And he tried a formula for Mars where the speed was proportional to 1 over the distance, an inverse relationship, so slower the further away the planet was. But no matter what he tried, he couldn't get that to work out until he started to use ellipses for the orbits. And with an ellipse, the sun at one of the focal points of the ellipse, suddenly everything started to work. And the planet would move around the ellipse. It would move faster when it was at perihelion, the near point, the nearest approach to the sun, and then slow down again as it moved away to the further point. In fact, with his second law, he went further and figured out that a planet sweeps out an area of the ellipse that is equal in equal times, no matter which part of its orbit it is on. And So the planet moves more slowly when it's further away and more quickly when it's nearby, but the area of those triangles, the short fat one or the long thin one there, is equal regardless of where you happen to be in the orbit. So that's his second law. And it's actually an example of the conservation of angular momentum. Now, his third law worked out that the time squared, the orbital period squared, is proportional to the cube of the distance. Now, you can actually prove this quite easily from Newton's laws, which we'll come on to in a moment. And it's a little job that I get my students that I teach GCSE to sometimes to do in their mathematics. It's quite a nice little worked example. It means that you can draw a nice plot of the periods of the orbits and the semi-major axis, the long axis of the ellipse. If you plot them against each other using a logarithmic plot like this, then you see they fit a straight line very, very accurately, and the slope of that line is 2/3, which tells you, given that it's a log-log plot, that the power law is t squared is proportional to d cubed. So those are Kepler's laws, which told us about planets. Well, what's that got to do with where I started with pendulums? Well, let's have a look. A pendulum moves slowly at the top of its swing and fast at the bottom. And planets move slowly when they're far away from the star, but they speed up as they whiz past the near point, the perihelion, and then slow down again. So they're doing the same thing as the pendulum, moving slowly when they're highest in the gravity field and fastest when they're lowest. So the stage was really set for that man to come and figure everything out, the man with the falling apple story, enter Isaac Newton. And a nice little story about this is he was having conversations with Robert Hooke, and didn't really get on very well with Robert Hooke, but he was arguing about the appearance of a comet in 1680 to 81. And this was really the trigger for Newton to go and figure out what was going on. He was provoked by Edmund Halley and Sir Christopher Wren and a small bet. And they bet that Robert Hooke, who claimed to have the proof, couldn't come up with it. And Newton said he had it, but he disappeared for 3 years and eventually came back and proved that an elliptical orbit must result if the force acting from the center is proportional to the inverse square of the distance. And it's that rule that allows you to prove all of Kepler's laws as well. Now, to do it, he had to invent the whole of calculus, differential calculus, and he published it all in the book. I say he published it, actually Edmund Halley published the book for him and was probably the motivating force in getting Newton to finish the book and get it out there. And that book is Philosophiae Naturalis Principia Mathematica, or Principia for short, and probably changed the world more than almost any other. But it wasn't the last word on this subject. Pierre-Simon LAPLACE came along and built on Newton's laws, extending the mathematics to try and work out the finer points of the orbits. And in particular, he was looking at some outstanding problems. They'd noticed by very careful observation that Jupiter's orbit was shrinking and Saturn's orbit was growing. And perhaps that's a little bit disturbing, because if that continued, then Jupiter would sweep in and probably destroy, or at least disrupt, the inner solar system. But in 1763, Laplace was able to show that it was all part of a 929-year-long cycle. And I like this chart here, which shows the variations in the period of Jupiter's orbit and Saturn's orbit, and also the little wobbles on top of both, which are actually the results of all of the other interactions with the other planets. But you can see the main effect is Jupiter and Saturn swapping energy between each other and then swapping back again in this cycle that was discovered. And the good news was that it meant that the solar system was stable in the long run, and that we weren't going to have a giant planet sweeping into the inner solar system and destroying the Earth. But if you remember that graph just for a moment, and we then look back to the story of the pendulum, this is a little experiment that you can do with a roller and some paper and a pendulum that's dropping sand or ink or something. If you roll the paper past the pendulum at a constant speed, you'll get this same wavy line that comes out. And the reason for this all starts to relate to the energy of what's going on. In a pendulum, the energy swaps between the highest point of the swing, where the pendulum is stationary and has no kinetic energy, but has maximum potential energy. There's 100% stored potential energy at the end points of the swing there. At the bottom of the swing, where it's moving fastest, 100% of the energy is now being translated into the kinetic energy of motion. And you can chart that and see that you get a swapping backwards and forwards of energy between the two forms. The kinetic energy rises, reaches a maximum, and then comes back down, and vice versa. The potential energy goes in the opposite sense. So the energy is flowing backwards and forwards between those two forms. But it probably wouldn't surprise you that the total remains constant. That's the law of conservation of energy, after all. But a more surprising result is that on average over time, the kinetic energy is half of the total. Maybe that wouldn't surprise you, but you could do the mathematics quite easily and work out that if you just take the average level, then it comes out as half. And there's another illustration of that here. You can do the mathematics. It took me about 3 hours to do it. I won't go into it and bore you with it, but it does prove that the average of the kinetic energy is half of the total. And I'm droning on about that because it's important for us in a moment. Now, if we go to 1772, the next hero of this talk is Lagrange, and he started looking at what happens in more complicated situations where you have three bodies. And in particular, he was looking at the Earth, Moon, Sun three-body problem of the Moon's orbit and trying to solve it. And what he realized was that there was a theory called the virial theorem. It says that over time, the average of the total gravitational energy in any system, be it a planet orbiting a star, or a moon orbiting a planet, or a child on a swing here, or indeed Galileo's pendulum, will always be split 50-50 between the kinetic energy of motion and the potential energy, no matter what the complexity of the system. This is an example of how energy tends to follow an equipartition rule. If you give it a number of different forms into which it can spread, then in a stable system that remains the same over a long period of time and isn't evolving, then on average, the energy will spread itself equally between all the different forms. And that's the virial theorem. Right, so enough of the sort of theory and mathematics for a minute. Let's just look at some practical side of this. First thing we're going to do is answer this question. How do you weigh a galaxy? Nice picture of the Andromeda galaxy here. Now, the first thing you can note about the galaxy is brightness is probably equal to the number of stars in the galaxy multiplied by the average brightness of the stars. Fairly straightforward. But you might have to add in the effect of glowing gas, and you might have to worry about nebulas and dark nebulae blocking your line of sight and dimming due to the obscuring effect of dust. And you might allow for all of those and then come up with an estimate for the mass based on how many stars you think there are and the average mass of a star. And if you do all of those things, you can come up with a reasonable estimate for the mass of a galaxy. The other thing you can do with a galaxy is measure how fast it's rotating. So we can look at the stars orbiting around inside the galaxy and measure their speeds and check to see if they're obeying Kepler and Newton. And Rubin here had a go at doing this, and the way she did it was to use the Doppler effect. Stars that are moving towards us along the line of sight have their light blue shifted, and if they're moving away from us, their light gets red shifted. And we can detect that by looking at the spectral lines where different elements in the atmospheres of those stars absorb different wavelengths, and they will appear to move to the red or to the blue end depending on the velocity towards or away from us of the stars. So you can do that for a galaxy. Now, you couldn't do it for the one shown here very well because the stars are rotating around the center of this lovely spiral galaxy in the plane that we're looking at it using, and so there's not very much movement along the line of sight going on. But if you take one that's tilted more towards and away from us, then you will find that the side that is coming towards us is shifted to the blue, and the side that's going away shifted to the red, as illustrated in the bottom diagram there. And there's a graph of the amount of shift being plotted out there, overlaid on top of the color-coded image. Now, when we do this, we get a chart, and you can try and work out whether or not you think it complies with Kepler's laws for the motion, which says that things that are further away should orbit more slowly. And you have to allow for the fact that the only mass that you should take into account is the mass that's closer to the center of the galaxy than you are. And so if you do that and you work out how fast you think things ought to be moving in that galaxy, you'll get a curve represented by the dotted line there. So as you begin to move away from the center, the speed goes up because there's now more and more material nearer to the center than you are, and so its gravity is acting on you to pull you around the orbit. And then that reaches a peak as you head towards the outer edges of the galaxy, and then the diminishing distance starts to kick in and the curve falls away again. Unfortunately, the actual measurements shown here are two sets of measurements from starlight in the optical in yellow, and then further out looking at the movement not of stars but of clouds of hydrogen gas using 21 centimeter radio, follow a rather different curve which doesn't seem to be behaving. And this was a real surprise. But the idea that something was going on had also been arrived at earlier. This is a picture of the Coma cluster of galaxies. All these many galaxies in this picture. There's some large elliptical ones in the middle there, and the more you look, the more you see. There are loads and loads of smaller spiral galaxies. And we can understand the distance. They're 321 million light years approximately away from us in this huge cluster. There's two large elliptical ones right in the middle there, and there's a good 10 bright spiral galaxies. And in 1933, Fritz Zwicky decided to study this. Now, he wasn't a very nice man, apparently, and the gesture he's making at the top there is allegedly he was being rather derisory of his colleagues, saying that they were spherical idiots. In other words, it didn't matter which way you looked at them, they were still an idiot. I don't think that endeared him. It wasn't going to win friends and influence people. And so perhaps that's why this result that he came out with was ignored for quite a long time. What he did was estimated the masses of all of these galaxies, as we were talking about earlier. Based on their brightness, you can infer how much starlight there is, and therefore how many stars, and therefore get an idea of the total amount of mass. He also looked at their movement using the Doppler shift again, and found that they were moving too fast. The cluster should have flown apart long ago. The galaxies were moving way too fast to be constrained by the amount of gravity that he was able to attribute to the mass of all of the galaxies. So he wondered what was holding this together. And it was a question of looking at the energies. You can balance up the energies of movement, the kinetic energy of movement, and there's the formula for it, half mv squared, half the mass times the speed squared. So we could get at that by measuring the speed of the galaxies and their masses. We can also estimate the gravitational potential energy. There's the formula for that. Potential energy is mgh, the mass times the height times the overall strength of gravity. A little bit more complicated than that in reality to do, but never mind. And this just depends on the position and the masses of the galaxies is the point. And what he realized was that using the virial theorem that we talked about, if the cluster was stable in the long run, then half of the energy ought to be, on average, in kinetic energy, and half of it ought to be in potential energy. So at any given moment, you would expect the most likely outcome was a 50-50 distribution of energy between those possibilities. However, when he worked it out, all of the mathematics, he was out by a factor of 10, a small, insignificant factor. And he wondered how you could possibly have got it wrong. And the direction of getting it wrong was that there was way more mass than could possibly be accounted for by all of the visible material in the galaxy cluster. And he even allowed for all the dust and darker material and all of the really hot gas between the galaxies, made an estimate for that. And he figured that there must be something out there that we can't see, and came up with the name dark matter for it, which is the topic really of this talk. And he really wondered, could there really be that much of this strange stuff that we can't see? A factor of 10 more dark matter, this mysterious substance, whatever it was? Or are we just making a mistake? So first of all, could this dark matter be dust? Could it just be dust blocking the line of sight to stars, making us underestimate the mass of these distant galaxies? Well, the problem with that is that over millions of years, dust would be absorbing the light and thereby blocking our line of sight to the stars and accounting for why we were underestimating them, but it would heat the dust up. And so we would start to see that dust glowing in the infrared part of the spectrum as it warmed up. And we just don't. We can look with our infrared telescopes, so we can rule out any intervening dirt and dust blocking the line of sight and dimming these galaxies. Next possibility was black holes. Well, black holes are not directly visible, and such dense things, however, would create gravitational lenses. One of Einstein's predictions would be that if you have a black hole in the line of sight between your telescope and a star, it will bend the light around it, and if the alignment is perfect, you will get a double image, or indeed a ring in 3 dimensions. This works to produce a 2D ring called an Einstein ring that you would observe instead of just a single image of the star. And so you would certainly see distortions of distant objects, and you could tell if there were that many black holes in the line of sight that were causing you to underestimate the mass of these clusters of galaxies. Now, when we do this, we point telescopes directly towards our galactic center, where there are millions and millions and millions of potential stars that could be gravitationally lensed by wandering black holes. So there's lots of opportunities for this to happen. We really don't see very many. We don't see anything like the number of these gravitational microlensing events. So our galaxy, at least, is not stuffed full of wandering black holes, something that I'm sure you're probably quite pleased to hear, because we wouldn't really want that. It'd be very, very dangerous to have that many black holes wandering around, accounting for 9/10 the mass of our galaxy, perhaps. And if it's true in our galaxy, it's probably true in the others, goes the argument. Now, we called these things massive compact halo objects, or MACHOs. It's always good to make up a ridiculous acronym for these things, but the reason they made up MACHOs for anything that behaved like a black hole, that was a very dense lump of matter, was because the other explanation for what dark matter might be was WIMPs. So you had WIMPs and MACHOs. And this idea is that perhaps there are undiscovered subatomic particles that might exist, but we have not been able to detect them and we don't see them. The name WIMP comes from weakly interacting massive particle, and the clue, apart from massive, it obviously needs to be a massive particle in order to account for this missing mass, but it needs to be weakly interacting. What's that all about? Well, the universe seems to have four fundamental forces in it. It has the strong nuclear force that holds the nucleus of an atom together. It holds the neutrons and the protons together. And if we assign that the strength 1, then the second strongest force is the one underneath it, the electromagnetic force, which keeps the electrons in orbit around those nuclei and is responsible for the vast majority of what we see around us. Chemistry, physics of real objects is mostly dominated by the clouds of electrons in the atoms that things are made of. And that is 1/137th, approximately, times the strength of the strong force. So a little bit weaker, but not excessively so. Now, the big difference between the two really is that the strong force has a range limit of 10 to the minus 15 of a meter, and really doesn't act outside the domain of the atomic nucleus at all, whereas electromagnetism, well, it can traverse the whole of the universe. Now, the third force is the weak force, which is responsible for radioactivity, whereby nuclei spit out neutrinos and positrons and other particles and decay. And that is 1,000,000 times weaker than the strong nuclear force, so 10 to the minus 6 in the strength box there. And also has a very short range, even shorter than the strong force, 10 to the minus 18 of a meter, 1/10 the diameter of a proton. Unbelievably short. And last and weakest of all the forces turns out to be gravity. The force between two particles has a strength on this same scale of 6 times 10 to the minus 39. That's ludicrous. It's nearly 40 orders of magnitude weaker than the strong force. It has an infinite range, and the crucial thing about gravity is that it's always attractive. All masses, be they matter or antimatter or anything, always attract each other. Whereas things like the electromagnetic force, you have both positive and negative charges, and whilst opposite charges attract each other, like charges repel. And so if you have a body that's electrically neutral, it cancels out that electromagnetic force, whereas there is no cancelling gravity. Now, dark matter turns out to be truly transparent to all forms of electromagnetic radiation. So it doesn't respond to the electromagnetic force at all. Light, radio, gamma rays will all go straight through it and pass right on through as if there was nothing there. And that's what they mean by weakly interacting. It also means that it's not interacting with the strong force, It might interact with the weak force, it may well do so, and it certainly has to interact with gravity because it has mass, and that's the whole point of the hypothesis of dark matter, is that it must interact with gravity. So we know it doesn't interact with the first two, certainly interacts with the bottom one, but it does or does not interact with the weak force, and nobody's entirely sure yet. Okay, so that's the fundamental point about weakly interacting. A WIMP, one of these hypothetical particles, would just interact with those bottom two and would completely ignore the electromagnetic and strong force. And the biggest piece of evidence that I think we have that explains all of this, brings a lot of these ideas together, and it's embodied in this one image, the image of the bullet cluster. What we have here are two galaxy clusters, one larger one on the left and a smaller one on the right. And they have collided with each other. And in fact, when galaxies collide with each other, the galaxies are so far apart compared to their own size, they don't tend to hit each other. The two clusters tend to fall right through each other and keep on going. And that's what's happened here. In the blue coloured zones, on the left, you can see one of the clusters of galaxies, and the other smaller one is over there on the right. So this is after the collision, these two clusters here, okay? What we've marked in the pink, the red colour, is hot gas. That's X-ray emissions. Now, blue has been marked where the mass of the system is. So the clusters are where the arrows point, the yellow arrows. The gas is where the X-rays are coming from, is where the red arrows are pointing, but the blue areas there are where the mass is measured to be, okay? And the mass is measured by looking at how the clusters of galaxies have, through their mass of the whole galaxy, caused a lensing effect, an Einstein gravitational lensing effect, on the far distant galaxies in the background, the much redder ones. There's one that you can just make out just here where the mouse pointer is pointing, which is a gravitationally lensed galaxy in the background. But there's another bit here, there are various other bits. And from the amount that those images have been distorted, you can work out how much mass there is in the galaxy cluster and even its distribution. And that's been indicated by where they've coloured it in blue. So what's happened is that the two clusters have fallen through each other. But the stars and galaxies have kept on going. No direct hits have occurred, and it takes a direct hit to stop them. So they've sailed on through, they fell under gravity, picked up speed, and then climbed the gravity hill the other side and slowed down again, just as a pendulum would. But hot gas can't do that because it's a continuous object. The two clouds of hot gas that belong to the galaxies have hit each other and slowed each other down. And that is why the red pinky areas there have been left behind by their original parent galaxies. They've suffered drag and been slowed down. But the mass has gone with the galaxies. All of the matter must therefore have not been in the form of gas or dust or diffuse objects. And it's not in the galaxies because we can estimate their mass from their brightness. It's in the form of dark matter, and it's fallen right through without being slowed down. So it didn't interact with itself by anything other than gravity or the weak interaction, perhaps. Nothing slowed it down, and it would have been the electromagnetic interactions that slowed it down. So this is extremely strong evidence that it is this particular type of matter. Now we have our Milky Way galaxy, and we have the ability to trace what's going on outside it in the form of the debris left from where the Milky Way galaxy has been eating dwarf galaxies for breakfast and leaving tidal tails behind around the outside of the Milky Way. And that also allows us to get a feel for the mass of the Milky Way galaxy and work out where that mass is in the form of the dark matter halo, which must extend way out around the outside of the Milky Way itself in quite a large ellipsoid there. And that explains those orbital velocities of stars and the fact that you have to go a very long way outside the galaxy before you are far enough away that you are outside all of the mass, and therefore Kepler's laws start to apply properly. Well, what about other explanations? Well, other people have tried many times, and perhaps one of the most popular attempts at coming up with a different physical theory that says that Newton isn't quite right about all of this. And one of them is Mordecai Milgrom here with his theory called MOND, which stands for Modified Newtonian Dynamics. And the idea is that a small change, an extra term in Newton's laws of gravity can be allowed when the acceleration is very low to just give that extra effect to gravity to account for the rotation of the orbits of galaxies and galaxy clusters, and thereby remove the need for dark matter. It's an attempt to modify the laws to fit the observations. Now, of course, this is what scientists are supposed to do. We're not supposed to stick doggedly to the theories of Isaac Newton when all the observations are telling us that the theory doesn't fit the data. We're supposed to change our theories, aren't we? And it's amazing how scientists are so stubborn that they don't do that. Now, Mordecai's theorem has made some quite successful predictions and quite a good fit to a lot of observations. So it's not a completely crackpot idea. But just recently, this little tiny dwarf galaxy has been discovered. Goes by the number DF2. And it's 65 million light years away from us, and they've managed to measure the orbital speed of the stars in this little dwarf galaxy. And it matches the orbital speeds that Kepler's laws would show without there being any dark matter. Now, this turns out to be proof of dark matter, in the sense that it rules out all the other theories of modified gravity, because a theory that says that gravity behaves differently just in the presence of normal matter can't explain a galaxy that behaves according to Kepler's laws like this. It's a slightly tricky point. No such modified gravity theory can just say, oh, well, in this particular case, it behaves like Newton, but in all the other cases, gravity is modified to behave differently. Whereas the dark matter theory can say, oh, it's fine. This dwarf galaxy just doesn't have any dark matter in it. Somehow the dark matter has become separated from all of the stars. Perhaps there's been a gravitational interaction with a larger neighbor at some point, and all the dark matter and stars have been stripped away. So this particular galaxy doesn't have any dark matter, but it can't not have any extra gravity. I hope that point's clear. It's a very, very strong argument. Now, we've also looked at large-scale structure of the universe using things like the Digital Sky Survey from Sloan to map the structure of the huge area of the universe. Now, it hasn't observed the bits where the data is not marked as black there, but the other filamentary structures going way out across the universe are the organization of clusters of galaxies, and the color represents how dense those clusters are. So the red bits are the dense bits and the greeny yellow bits less dense. And then you've got huge dark voids between the galaxies. And when we run computer simulations of how gravity would form the large scale structure of the universe, starting off with what we think the conditions were like after the Big Bang, we have to plug 90% dark matter into the equations. Otherwise, these filamentary structures that we observe just don't turn up in our simulations. Whereas if we do assume dark matter, then the simulations come out to look just like this and match extremely well. So it's very strong evidence that there must be this extra mass in the universe. Basically, if there wasn't the dark matter, then the structure of the universe would take much, much longer to pull everything together into these knots and lumps and filaments. We would end up with a largely smooth and empty universe. And it can also actually use the presence or absence of the distorting effect caused by Einstein's gravitational lensing to map where the dark matter is in the universe and effectively do a CT scan of the universe over time and over 2 dimensions of space and work out a 3D model of where the dark matter is in the universe. And this is the picture. Now, this takes a little bit of explaining. We have time going from the left to right, and the 2-dimensional slice of the density of dark matter starts at the left in oldest times and then moves over progressively more and more modern times to the right until the present time at the right-hand end of the diagram. And what you can see is that gradually over time, the right-hand end of that looks much clumpier with big voids and rather dense regions, whereas the older, further to the left you go, the more that the dark matter is more evenly spread out. And so it shows that over time, gravity is making that dark matter clumpier and clumpier as the self-gravity of everything is pulling it in tighter and tighter. And that fits the simulations as well. So I'm very confident that there is this substance called dark matter out there, and that one day we're going to find out what it's made of, and that will be very, very exciting and interesting indeed, because it's not part of any of our standard particle theories. Now, indeed, people are trying to go and find dark matter and trap it. And this is the ice cube experiment at the South Pole. At least this is the building on top of it, because there is a cubic kilometre of transparent, super clear ice below this machine here. And it's full of lots of little optical sensors looking for the flash of light caused by neutrinos coming in from all directions and hitting very, very occasionally, because neutrinos are a type of weakly interacting particle. They only interact by gravity, having very low mass. That's very insignificant. And by the weak force, they're a product of the weak force in radioactivity. And so occasionally they hit the nucleus of an atom and they cause a little flash of light from the recoil. And that's what IceCube is looking for. But it's also looking to see if incoming dark matter particles might crash into ordinary matter and interact with it through that weak force and cause a similar but detectably different flash from the neutrinos. And so far, They have found nothing at all. Also doing experiments in deep mine shafts over in the States, looking for dark matter. This is the LZ dark matter experiment, which is a giant tub of liquid xenon, a mile underground, kept very cold indeed, looking again for those flashes of light of the recoil when a WIMP, a particle of dark matter, hits the nucleus of a xenon atom in the liquid. And in theory, it should produce a flash of light, and we should be able to detect it. So far, nothing found. And this is the third experiment. Deep in a mine in Minnesota, they're using germanium crystals, and the guy in the suit is getting the equipment together. And this is going to be cooled right down to near absolute zero. And listen for the sound waves produced by dark matter interacting with ordinary matter in these crystals as it goes through. It's going to be at 10 millionths of a degree above absolute zero. Unbelievably cold, but no results yet. And you're probably all familiar with this picture, the cosmic microwave background radiation. And this too has something to say as regards evidence for dark matter. It's the heat signature left over from the Big Bang. Started off at the temperature of the surface of a star at about 3,000 or 4,000 degrees when it was emitted, this light, when the universe first became transparent about 380,000 years after the Big Bang. It had cooled enough for the electrons to bind to the nuclei and form neutral atoms, and that let the electromagnetic radiation loose through the universe as it became transparent to it. Nowadays, because of the expansion of the universe, the wavelength has been stretched right out into the microwave, and so we see the effective temperature of it not as 3,000 or 4,000 degrees, but 2.7 degrees above absolute zero. And there are tiny, tiny 1 part in 100,000 fluctuations in that temperature as we look in different directions across the sky. Occasional cold spots and hot spots, but they're very, very minor. But if we look at the structure of those cold spots and see how big the ripples in that pattern are, then this can only come out right in our simulations and our models of the earliest stages of the universe if dark matter was present. So again, another whole strand of evidence pointing towards that there really is this stuff out there, even though we just haven't managed to detect it yet. And gravity waves, the Laser Interferometer Gravity Wave Observatory, LIGO, you probably heard that it detected the merger of some 30 solar mass black holes as they spun in a spiral towards each other and merged together. Now, we're quite curious as to the origin of these black holes, because stars, when they collapse in type 2 supernovae and compress their cores down, tend to produce black holes of a few solar masses, whereas galaxies in their centers tend to have supermassive black holes that have the mass of maybe 1 million or even 1 billion solar masses. So where do these intermediate 10s, 20s, 30s, 40s of solar masses, black holes that we are detecting, come from? Are they left over from the original formation of the universe, leftovers of the Big Bang? Are they perhaps the product of dark matter black holes forming in that earliest possible time? We just don't know. It's a very interesting subject indeed. And furthermore, we can look at the cosmic microwave background radiation in extreme detail and see a pattern embodied on it, which look like those dark matter black holes might be casting shadows. You can see that in the image on the right that has been enhanced. Those grey blotchy areas could be the shadows cast by dark matter black holes from the Big Bang, where they're blocking out the light of the original cosmic microwave background. Now we need to study these in more detail, and the Euclid telescope was due to go up this year and to go to look for lots more of these micro-lensing events caused by dark holes, dark matter black holes. And we haven't had the results for that yet, so I'm eagerly awaiting finding out more about this, and maybe we can start to get a handle on and solve the puzzle. So thank you very much for listening. That's from the pendulum to dark matter, all the evidence that we have that leads us to believe that there is this mystery substance out there in the universe that you can't see, smell or touch. And yet we have never managed to put our finger on it and detect it, despite our best efforts. It's quite a puzzle.